So here I will be introducing the Scramjet Inlet, and just like other kind of inlet, the Scramjet Inlet also aiming to minimize total pressure loss, stabilize the mass flow to the engine, and minimize mass flow slippage, which means it's captured more more as possible of the air flow. And specifically for Scramjet engine inlet, you need to compress the airflow because there is no combustor in the scramjet. And there are three types of scramjet inlet. First one is external compression inlet. Second one is internal compression inlet. And also there is a mixed compression inlet. So here I will be most talking about the design of scramjet inlet. So first, there are many kinds of methods to design the scramjet of inlet. So I will talk about two methods for designing mixed compression inlet here. So the first method is aiming to get maximum pressure recovery, and in this method, oblique shock angles and one terminal normal shock angle were obtained using gas dynamic relations and Lagrange multiplier. And also from the Ashworth criterion, shock should have equal strength to get larger total pressure recovery. And also increasing the number of shock waves will also help to get a larger total pressure recovery. And another approach is aiming to prescribe to get a prescribed Mach number at the beginning of the accelerator. And for this kind of method, the separation region and inlet start issue were considered as the most important issue. And also there are other peoples aiming to combine these two methods together for to get a better and new approach to design mixed compression inlet. So also like inlet design would seriously affect by the compression would seriously affect compression performance, combustor performance. When optimizing the inlet design, combustor performance will also be considered. The experiment there's experiment is designed to investigate the influence of inlet geometry on the flow and the combustion dynamic. And from the experimental results, the increasing of compression angle and contraction ratio would improve the combustion intensity and stability. However, it will also cause strong shock wave and increasing the risk of unstart inlet, and this will all increase the total pressure loss. So this experimental suggests that people to consider both the overall system efficiency and also the compression dynamic to optimize the inlet geometry under certain flight conditions. And also there's a new idea for the scramjet. So in order to let scramjet can be used on normal aircraft from takeoff to landing, like the whole uh, mission of the aircraft. There is a new design called combined cycle engine need to be used. So here there is a three dot hypersonic inward-turning inlet has been designed for this combined cycle engine. And it is just using a single rotational flap on the compression side. And for this kind of inlet, there are three flight and working modes. The first one is called pure scramjet mode, which open only the scramjet parts. And so it works for Mark from 4 to 6. And there's another mode called dual dark mode. And in this mode, both injector and scramjet inlet will be turned on. It is used to ensure the larger throat area, which ensuring the inlet stability. And this works for Mark from 2 to 4. And the last mode is turbojet mode. It will turn on only the turbojet parts, and the other two parts, which are injector and scramjet parts, are open for spillage. It's not simply just closed. And this kind of mode works for Mark below too. But the performance of this combined cycle engine is not great and stable for now. So there's a paper done some simulation on this kind of trade-out hypersonic inlet, and it suggests that more work needs to be done to determine the distribution of mass flow into these three different parts, which influence the performance of this inlet really seriously. So, and also experimental experiments need to be done for further analysis instead of pure simulation. If you want, we actually want this engine to be manufactured and used.